All right, today we want to talk about something known as an inverse trigonometric functions. What do we remember about inverse functions from all the way back in our first chapter of this course? Oh boy. So it sounds like when I say inverse trigonometric functions, we need to talk about what that does. But we may need to remind ourselves, what do inverse functions do in general? What are some properties of inverse functions as opposed to the original function? We need to kind of look at that idea. And then we need to look at how we notate this concept of an inverse function and what it might be able to tell us when we get all the way said and done. So there are some details we need to provide. And since nobody seems to be rustling through their notes or their book to find out what an inverse function is, at this point in time, that's a reciprocal. 1 over the function is a reciprocal of the function. Depending on your kind of function, that may be sufficient to be the inverse itself. But that is not true about trig functions. 1 divided by the function is not the inverse of a trig function. It's a reciprocal. It is a reflection across the line y equals x. That's one of the techniques, or one of the things we talked about way back at the beginning of the year, is that when you have a function and you reflect it across the line y equals x, that reflection, as long as the reflection is a function, is now the inverse function.
Has to be 1 to 1 too.
Oh, so that's an important concept. It has to be a 1-to-1 function to have an inverse. Now, there's some good math terms up there. That does not mean we know the definition of what it means to be a 1-to-1 function. It doesn't mean that we can really quickly say, oh, I know how to figure this out. So let's go back to our bell work, because we want to start with some of this information. We have the sine of x function here, the tangent of x function here, and the cosine of x function here. As you consider all three of these functions, would you consider any of them 1-to-1? I have one no. Some yeses. Raise your hands. How many say no, they're not 1-to-1? So I have one no. Okay. How many say yes, they are 1-to-1? I've got 3, 4. How many go, I don't have a clue if it's 1-to-1 or not? And there's the majority. Because you're going to vote on something, right? Let's go back and think for a minute. Is there a way, visually, that we can try to decipher if something is 1-to-1 or not? A vertical line test tells us about, is it a function or not? But there's a horizontal line test that talks about, is it 1-to-1 or not? So let's take a look. Now the tangent function down here.
I forgot it's for every single line, not just.
Now if it's a 1-to-1 function, if I do this horizontal line through here, how many times am I supposed to touch the original function for it to be 1-to-1? 1. I don't think 7 quite makes the muster. How many times did I touch down here on the tangent?
Not 1.
You're right, not 1. And notice, I just did a limited bit of a domain. I didn't do the entire curve. This is supposed to keep going in the same pattern in both directions. So there's an infinite number of intersections. What about up here? Is that 1-to-1?
No.
How many times do I do it? Again, because I have arrows on the end, it is an infinite number of meanings. Just out of curiosity, because I think I know the answer already, but just to confirm, what about the cosine function? Is it 1-to-1?
No.
It is not 1-to-1. Oh boy. So, for us to determine the inverse, one of the techniques we need to look into is this thing 1-to-1? So now we need to contemplate, how do we make that decision happen? All right. I paused there for a second. We had an interruption. Coming back to this. Somebody alluded to, and maybe on the last little segment, what do we need to do to make this thing become one-to-one? It's called a domain restriction. So let's talk a little bit about some of the rules that we will utilize to help us create a correct domain restriction. If you were going to restrict the domain of this function, would you need to be able to use every y number that the function actually graphs? Meaning from -1 all the way up to and including +1. Would you need to have those numbers in this graph included?
Yes.
Okay? So that's going to be one of our criteria. We need to be able to pick a domain restriction that includes every y number available. Would it make sense that you would pick a domain that we call continuous, meaning I pick a spot and I keep going and then I stop and I'm going to use only that spot, so I'll create a little box. So maybe kind of like a box like this. Would that be a way to say, oh, I'm going to restrict the domain? Now, my box, is it a little too big?
Like,
I got close to picking all the y numbers, but I have a little bit extra. So this, again, is not a true domain restriction, but it is what we call continuous as a domain restriction. Let's see if I can move this thing a little bit. What about that? It's not good, huh? What do you think about that one? It's pretty close.
I think it's on the downwards, so I'm going to have to give it a no.
You have to give it okay. So it's not quite good enough. We're going to be particular. We want to kind of go to maybe closer to there. You like that a little better? Okay. It's good to have a critical eye on these things. We want to make sure we're picking good things. Now, there's a third criteria that we're going to try to work with when we're talking about domain restrictions. And that criteria happens to be that as much as possible, we want to be near the origin as part of our existing domain. Can you tell, based on where this x-axis has been labeled, am I near the origin? Near is not a very good math term, is it? Yeah, that's right. It's not a really good math term. Let's see if we can contemplate the math term being include the origin. I haven't done that, have I? Do you think I can rewrite this particular domain restriction to include the origin? Well, let's take a look. Maybe I can move this thing in a little different way. Hey, look at that. Does that include the origin?
No.
We're getting pretty close now. In fact, I want to be here. I really want to be here. Now, my drawing is a little bit off. You know that at -pi/2, we're down here at -1. And you know at +pi/2, we're up here at +1. So my actual curve is a little off. If I have a region that looks something like this, where I'm going from -pi/2 to +pi/2, have I included all possible y numbers? I go from -1 as a y number up to +1 as a y number. Did I include the origin as part of this?
Yeah.
Okay. And this curve is continuous in this range, correct? Okay. So it has all the pieces and the parts that we want to consider when we're talking about an inverse function. Here's what that means. For y equals the sine of x, the domain restriction is x is an element of it's called a closed interval, meaning I include both in numbers as values I calculate, -pi/2 to +pi/2, and only that set of numbers. So it very much restricts the image. Okay? This is my domain restriction for the sine of x function. guess what? We get to do the same thing for the tangent of x function and the cosine of x function. Aren't we thrilled?
Yeah.
I can see it right on your faces. Everybody got this written down?
No.
Hurry up. Yes, negative pi over 2 to positive pi over 2. The interval. That's brackets, so it includes them. And any questions? All right, here we go. Wait.
Yeah, you can do
I think we're ready. So when we look at the tangent function, we've already discussed that it's currently not one-to-one. I did slide those up earlier. It needs to be right there. Is there a region where we're including the origin and we're including all possible y values in that region? Yes, sir.
Just the same negative pi over 2.
I do have one question for you, though. Because the vertical asymptotes occur at negative pi over 2 and at positive pi over 2, will I actually include the negative pi over 2 and the positive pi over 2 in the interval for tangents? No, because I don't have a value there. So when we're talking about for y equals the tangent of x, the domain, restriction, is x is an element of the interval with parentheses, not brackets, of negative pi over 2 to positive pi over 2. Parentheses. So we do not include the ends. Does that make sense? Okay. We're doing good. We got 2 of the 3 of them, right? So if I leave you on your own to guess for the cosine function, take a look at your bell work. If you look it over, do you have an idea what might make some sense as a domain restriction for the cosine function?
Will it have to go out until negative pi and pi?
Well, let's take a look. You said negative pi to pi. That's what I heard, right?
negative 0
If I go that far, is it 1-to-1?
Because you have to include all ranges of y.
I do have to include, and I did include all ranges of y, because I had the 1 included, had the negative 1 included, had the negative 1 included. But the question is, does it pass that horizontal line test? So is it 1-to-1 in an interval from negative pi to pi? See, there's a horizontal line I could draw, and I touch it here, and I touch it. That's not 1-to-1.
Would it be negative pi to 0?
Let's take a look. Let's see if I can shrink this side. It's a little bit I can. Now, question is, do we have a 1-to-1 representation here? Okay. Do we have all possible y answers represented here? Okay. Are we including 0 here?
Yeah.
There's only one problem with this. It's all negative. Nothing wrong otherwise other than it's all negative. And mathematicians a lot of times don't want to have just negative answers show up every single time. So how do we fix that problem?
0 to pi.
So if I move it over here and go from 0 to pi, do I still have every y number used one time? Do I still have a one-to-one function? Okay, and I'm including the 0 in this, correct? So does this meet our criteria? It's just kind of, we have positive answers. And I know you like to deal with positive answers more often than you like to deal with negative answers. Is that correct? Okay. So this is what we're going to do for the cosine function. And notice how it's different. It doesn't go from negative pi over 2 to positive pi over 2. And notice why it's different. Because for the curve is shifted, and then we have to cover all these values. So if I am thinking about a domain restriction for the cosine function, I'm going to include, again, the endpoints, because I don't have asymptotes, and 0 out to pi. There's my domain restrictions. Oh, why is this so important? What's significant about knowing the domain restrictions? Oh, so what you're telling me is then when I get answers out of the inverse function, my answers are only in this region. Or my answers are only in this region. Or my answers are only in this region. Is that what you're telling me? That's what the answers are for the inverse, yes. Okay, so here's a different question for you. Can you tell me what is the range of the sine function? How far up and down do the sine numbers go? Excellent. And we include both numbers, correct? Because we can touch -1 and we can touch +1. Is that right? All right. What about the tangent? Do we know the range of the tangent? Yes. It goes all the way up and down. All the numbers we can imagine that are real. The range. What about the cosine function? So we've already done this one, haven't we? Okay. And you're telling me that when we find the inverse, we switch the domain and range. So with the inverse, the domain is this, and the range is this. Or the inverse, the domain is this, and the range is this, and so on. Right? So these things are kind of important, right? Okay. Exciting stuff. Tell me.